Hi, my name is Yannik Thomas, and I work at Norfolk Southern, or NS. I appreciate Kaylee's introduction, but I'm absolutely not going to say a single word about the merger today. But I am going to talk about technology. So, as most of you hopefully know, NS is a railroad, one of the biggest in the country. We are 20,000 men and women that operate about 19,200 miles of railroad in 22 states and about 260 yards of various sizes. We serve 42 intermodal terminals and ports and 40 automotive ramps, and we move over 7 million shipments of freight per year. We transport primary commodities like coal and grain and lumber products and bulk liquids. We also carry intermediate and finished goods like coiled steel and finished vehicles. In intermodal containers, we move just about anything you can find on a Walmart shelf. In other words, we are a large, complex, and highly interconnected operation. And we've been doing it since about 1827. So I wanted to talk about how we think about innovation and building technology products for our business. Even though we've been at this for 198 years, many of our railroaders, including me, are involved in finding new ways to apply technology to make our operations safer, more reliable, and more efficient. I'll talk about some of the cool things we're working on, and I'll try to distill a couple of principles, 3 principles, about what I've learned about successfully innovating at NS. And maybe, just maybe, some of those principles are applicable to other large, complex, and interconnected operations. Before I start with what we do at NS, I wanted to tell you a story. A true story about something that happened across the Atlantic on a different railroad just under 30 years ago, on Deutsche Bahn, the national railway company of Germany. On June 3rd, 1998, passengers traveling on a high-speed train between Munich and Hamburg were shocked when a strip of metal entered their passenger cabin in the first car off the train and got lodged between 2 seats. The occupants of the rail car screamed and fled to find the conductor, probably relieved to have avoided an injury from the piece of metal that entered the cabin. Little did they know that they were just a few minutes away from one of the worst rail disasters in modern history. Minutes after that piece of metal entered the cabin, the conductor was found, and he quickly walked up from the 3rd car off the train to the 1st car to inspect the damage. Just about as he was getting there, the train violently derailed, starting with the 3rd car. The locomotive, the train had been near a bridge near the town of Eschede in Germany. The locomotive in the 1st passenger car went under the bridge. The 3rd car, the 2nd passenger car, derailed and hit the bridge at over 120 miles an hour, causing the bridge to start to collapse. Cars 4 and 5 were crushed by the bridge, and the rest of the cars in the back of the train plowed into them at 120 miles an hour. 2 Deutsche Bahn employees that were working under the bridge were instantly killed. In all, 101 passengers and crew were killed, and 87 were seriously injured. Investigators studied this for months, and what they found is that a flaw in the design of the wheel had caused it to crack and then break prematurely due to metal fatigue. When the break occurred at high speed, a strip of metal came off the wheel and lodged itself into the train. Half that piece of metal was inside the cabin, which the passengers saw. The other half was dragging along the track, and as it went along the railroad, it threw a switch inadvertently, and that caused cars 3 and on to go down a different track than the first 2 cars of the train. The Eschede disaster was investigated for many years. It was studied by railroaders, regulators, engineers, product component manufacturers, and it led to a lot of operational changes at Deutsche Bahn and at other companies. It also led to a lot of new techniques and guidelines on how to build wheels. The consequences at Eschede were so severe because of the high speeds involved on Germany's high-speed network. Those speeds largely don't exist here in North America, although I know that California is trying to build something similar. But even though the consequences may have been less catastrophic on our own cracked wheel and broken wheel derailments, even on low-speed trains, cracked wheels have remained an elusive enemy for nearly 30 years after the Eshita disaster. Traditionally, wheel cracks are small, often no wider than a human hair, and they can only really be detected through manual inspection. In most rail maintenance operations, humans visually inspect each wheel of a car as they enter and leave rail yards in all kinds of lighting conditions, and they look for many kinds of defects, including cracks. A single train, as it arrives or departs, can have over 1,000 wheels on it. So, as you can imagine, some hairline cracks could get missed by the human eye. The way that railroads have dealt with this risk over time is to create sophisticated operating practices developed over decades of fine-tuning to minimize the likelihood that a cracked wheel could lead to something catastrophic. But it would still be safer and more efficient and less disruptive if we could detect a crack and not rely on all of the operational safeguards that have to stop that crack from turning into a catastrophe. On January 15th of 2025, Norfolk Southern became the first railroad to autonomously detect a cracked wheel in a mainline production environment. Using high-speed cameras inside a specially built lighting portal, our technology takes over 100,000 images of each train as it passes at speeds up to 60 miles an hour. We capture over 50 pictures of each individual wheel. Near the portal, there's a bungalow where there's a GPU rack that processes 76 different algorithms. One of those algorithms is designed to identify cracked wheels. Every defect identified by the 76 algorithms is sent to an operations desk in Atlanta, which triages the defects and based on their criticality, and they take action. Critical defects, like a wheel crack, will cause the operations desk to tell the train crew to immediately pull the train into a siding so that the damaged rail car can be set out. Less severe defects, like a bent beam, will create a work order that'll be remedied at the next scheduled maintenance location. Since January 15th, we have run tens of thousands of trains, and across those tens of thousands of trains, we caught 46 hairline cracks that were not caught by human inspectors, some of which may have led to a derailment. We started working on machine vision to detect equipment defects in 2021. A team of data scientists at Norfolk Southern collaborated with our mechanical experts to develop the concepts and build a product. The hardware and camera expertise was supplied by a partner, the Georgia Tech Research Institute. Working together, this team built a rough prototype in 2022 using old shipping containers and ratchet straps. They tested and iterated their product outside of Norfolk Southern's Inman Yard in Atlanta, turning it into an operations-ready product we called Digital Train Inspection, or DTI. We had a major derailment on our railroad in 2023, and that firmed our resolve to get this product to market faster. And we put our first DTI portal in action in Latonia, Ohio, in September of 2023, just 20 miles where our derailment happened. We have now deployed these portals to 9 different sites and have plans to get to 17 in the very near term. Our DTI portals were not our first attempt to build rail inspection portals. Prior to building this product ourselves, we had tried to purchase vendor-built solutions. But we repeatedly found that unless we were in the driver's seat of building the product, we could never really get the fine-tuning we needed to be operationally successful. When the stakes are high, as they usually are in large, complex operations, there's little margin for error. Those of you that are familiar with machine vision will know that camera angles and lighting are critical to getting good results. With vendor-provided solutions, we found ourselves negotiating over change orders for the cameras or change orders for the bulbs inside the lights, instead of focusing on shipping a product that could change the operation as quickly as possible. That takes me to what I think is the first principle of innovating successfully at NS, which is that the hard part about building a product for a complex operation is the integration. It isn't exactly easy, but it is probably within the grasp of many young computer scientists and engineers to build an image classifier that identifies a cracked wheel. But it is several orders of magnitude more difficult to build a system for identifying broken wheels and cracked wheels in hundreds of trains at the same time, moving at 60 miles an hour in all weather conditions, in real time, with a good enough false positive rate to avoid disrupting the operation unnecessarily. Integration, in the broadest sense, integration within the system, integration between related systems, and integration into the operation. That's the hard part. Another product we built more recently, and one I was involved in deeply, is also an application of machine vision. I mentioned that NS serves 42 intermodal terminals, 27 of them operated by us. At large terminals, thousands of truckers come in and out every single day, dropping off and picking up containers and trailers. These truckers typically are assigned a parking space on the terminal for the container or trailer they are dropping off or picking up. Sometimes an assigned parking space is occupied unexpectedly, or sometimes a trucker makes a mistake and parks in a space that wasn't supposed to be theirs. Over the course of each day, this happens many times, and as these errors accumulate, what ends up happening is the terminal's data systems lose track of the position, the exact location of every piece of equipment on the terminal. In order to correct that, we do cycle counting on intermodal terminals on a daily basis. Cycle counting used to be done by humans driving around with paper and a clipboard. About 20 years ago, we gave them mobile handhelds that were connected to the data systems of the terminal, and that allowed them to do that activity of cycle counting faster and with fewer errors. Over the last 12 months, we built a product called Pulse that applies machine vision to automate the cycle counting process entirely. Working with a tech startup, we built Pulse using their machine vision API to recognize different types of equipment on a terminal and record the exact position and equipment IDs into a database. We built a magnetically mounted camera rig that can be attached to a pickup truck. And as that truck drives around the terminal, it passively updates the terminal's inventory. So we've gone from running 1 to 2 manual cycle counts a day to continuously running passive inventory updates autonomously, which gives us an order of magnitude better inventory accuracy with virtually no manual effort. Unlike a rail portal, a magnetic camera rig mounted on a pickup truck driving around is subject to unexpected lighting conditions and angles. So we rely on cutting-edge research from our startup partner and artificial intelligence techniques that they have to detect regardless of all of those variables. But even at the cutting edge, we trigger a 2% exception rate. That is when the algorithm does not know what it's looking at. For that 2% of cases, we built an exception pipeline that streams these to a desk where a human clerk can look at what it is and either correct the record or dispatch a terminal operator to go physically check out the piece of equipment. Having accurate terminal inventory dramatically reduces the seeking that truckers and our terminal operators have to do to look for a particular container or trailer. Taken over millions of pieces of freight over a year, this significantly reduces the amount of activity at the terminal to move a given amount of freight. And reducing activity makes us safer and more efficient, and it allows truckers to get in and out of the terminal a lot faster. So I mentioned that our first principle of innovation is that integration is the hard part. The second principle, which is quite related to the first, is that product management at NS, successful product management at NS, requires deep domain expertise. Our DTI product was managed by our mechanical team. They are the experts on detecting equipment defects and fixing them. Over the course of building the product, they guided thousands of choices about small and large decisions And those choices have allowed us to build a product that has truly transformed our operation. Our Pulse product, the terminal inventory product, was managed by a team that came from the intermodal operation. Every day, that team makes choices about what to prioritize, when to keep refining, and when to ship a product into production that is good enough for the operation. Each choice is informed by shared consciousness with the operation and all of the different stakeholders that it influences or is influenced by. Apart from making us safer and more efficient by reducing seeking activity, accurate inventory also allows us to automate the terminal. That leads me to a third cool product we're working on, which I'm particularly excited about, which is autonomous hostlers. Hostlers, or yard trucks, or yard jockeys, or shunt trucks, as different people call them, different things, are traditionally operated by human drivers. And they move containers and trailers around a terminal, for example, from trackside, where they have been unloaded off a train, to a parking lot that could be a mile and a half away. Autonomous hostlers, as the name suggests, don't need a human driver to move equipment around. Building them is, on one hand, significantly simpler than building autonomous trucks that operate on public roads that, of course, some companies are. But even though it's simpler than that problem, it's still a very, very complicated problem, and one that we are not well equipped to do as a railroad. So we partnered with another startup to build autonomy from scratch into a newly manufactured drive-by-wire hostler that'll be a proof of concept that, once refined, just like our container and ratchet strap proof of concept for the DTI portal, will be scaled across our system. Testing has shown, unsurprisingly, that autonomous yard operation is safer and has significantly fewer accidents. By automating hostlers, we can imagine a future where we divide an intermodal terminal into two zones. One where autonomous cranes and hostlers operate, and another valet zone where outside drivers can pick up and drop off containers or trailers. In that operation, a driver could make an appointment to pick up or drop off a container in a particular time window. The terminal's operating system would then dispatch a work order to an autonomous hostler to position that container or trailer in the valet zone at the optimal time. You can even imagine a scenario where a mobile app with the driver could update based on real-time traffic conditions in ETA, so that even if they're late, the terminal will have their container ready for them when they get there. I see that type of operation being a reality within the next decade. So that takes me to the third and final principle for driving innovation at NS, and that is that we work closely with partners to help us get to the cutting edge. We are experts on a lot of things, particularly a lot of things about running a railroad, but we can't be experts at everything, and certainly not at the cutting edge of technology, where recent events show that change is very rapid and the entire game can change in less than a year. But our approach to partnering is quite nuanced. We expect our partners to bring the most advanced techniques in the world to the table, but we still have to be the ones building the product. We have tried asking implementation consultants to execute a requirements document. That approach, we've found, scales poorly with the sophistication of the product you're trying to build and the complexity of the operation you're running. We've also tried buying products off the shelf to be customized by the vendor or by a third party. That approach does work pretty well for some products. Cases where our use of the product is very similar to the vendor's original vision of what that product is for. But it tends to create a lot of challenges and be more trouble than it's worth when you drift away from that original vision the vendor had when they built that product. The corollary to that observation is that where we have simple needs like managing our HR records or our CRM tool, we can rely on vendor software. But anywhere we touch the real complexity of our operation, whether it's detecting defective equipment, counting inventory on our intermodal terminals, or automating hostlers, we are typically better off being firmly in the driver's seat of building the product. There are a lot of great products that we have built that I don't have time to talk about in detail. One of those products, our continuous rail flaw detection system, has been so successful at detecting and escalating defects in the rail that 2024 became the first year where Norfolk Southern did not have a single mainline derailment caused by broken rail. We have built some of the world's most advanced graft optimization tools that my team uses on a daily basis to optimize the movement of traffic on the railroad. With the kind of compute that we have available today, we crunch trillions of solutions on a daily basis, something that even last year wasn't feasible. We've also had a bunch of, I won't call them failures, but learning opportunities. For example, we violated the second principle when we're over-optimistic about how much we could customize a vendor's tool as the operating system for running our automotive ramps. The system was originally built for automotive OEMs managing factory lots. And as we tried to customize that tool for a fairly different purpose, we ran into a lot of challenges. And it has been an uphill battle for the product team, the vendor, and the operation ever since. The result is that we probably need to think again about how we manage our automotive ramps. So there you have it. 3 principles that I've learned about innovating successfully at NS. Principles I suspect are applicable to a lot of large, complex operations. First, the hard part is the integration, in the broadest sense. Second, the product manager must be a deep domain expert. And third, we must rely on partners to bring us the world's most advanced science while keeping control of the product vision and priorities. Thank you for letting me share.